let's get this show on the road. Hello everyone and welcome back to our OpenGL math visualizer stream or series. Today we're going to be building upon the sphere that we looked at last time, so I'll just pull up what we rendered last time, or I guess the directional light that we looked at last time, and so it was just simply, I guess the rectangle is there, and this is our sphere. So I added the colors in here, so I just added the two VBOs, and that is, I need to show you guys actually. So yeah, I added two VBOs for the two different colors that we're passing in, the diffuse and the specular color, and this is what should be the output with a bronze sphere. So yeah, that was the sphere, and we're now going to be looking at how to create an arrow. So the arrow will serve the purpose of actually giving us some orientation. So once we get into looking at, sorry, give me 2 seconds. Once we get into surfaces and looking at more stuff where like transitions and stuff, we're going to want to be able to orient ourselves in respect to the world, just so that we can kind of check our results, just to make sure that we're doing everything properly. So we're going to create some arrows that we will be able to use, not for the express purpose of, but we will be able to use them for axes, which is just a vector. So we're going to be essentially creating a way to represent vectors in the 3D space. And yeah, so that'll be fun. So we're first going to go over what the math behind it. So, because there is a bit of linear algebra behind this. So let's look at what an arrow looks like. So it'll have a start point and an end point, and we're going to make it 3D. So we want it to have an arm like so, and then we also want it to have the arrow head. So that's going to look like that. So this is our start point, and this is our end point. Let's see if I can zoom in anymore. So those are the first two parameters, and then we also have a few other dimensional parameters. So the first one is going to be the arm radius. So that's just going to be the radius of the arm body. And then we're also going to have the head height. And we're going to want to specify the head height independently of how long the actual arrow is. So for example, if we made an arrow that was, say, 20 units long, and we made the head 1/20th of that, or 0.05 times the length, then that head would be 1 unit long, and that would be a lot. So we're just going to have that head height be something that's independent of the actual length, and we're just going to hard code it in world unit values. And we'll actually play around with this because it'll be pretty cool to see how we can extend the head beyond the start point and also beyond the end point by specifying a negative head height. And then we're also going to have a head radius. So the arm is essentially a cylinder, and the head is a cone. So the cylinder is also going to need a height, but given the start and the end points and the head height, we'll be able to determine this. So this length here is just the magnitude of end minus start minus the head height. So that can be derived from the rest of the parameters. So the cylinder has a height and a radius, and the head has a height and a radius as a cone. Now, we're going to have to figure out some way to transform this stuff, because we have a start and an end point, and they're not always going to be along some axis. So for example, if we just started with a base of, let's say this was along the y-axis. So this is j hat, and we have our arrow going from the origin, and let's just say it stops over here, like so. So our starts here, end is here, and then we have the other dimensional parameters. So this would be easy to represent. Well, we would just have all of the points in the base of the cylinder be in the xz plane. So this j hat, and this is I hat, and this is k hat. So all of the points in the base of the cylinder, I'm just using a crude circle there, but the cylinder would essentially be on the base of the, so that's I hat, and this is k hat, and then it points up, so the cylinder extends in the y direction, or the j hat direction. So the two vectors that define where the base of the cylinder will be, well, the plane containing the base is going to be the I and k hat vectors. So we're going to have to figure out, okay, well, this is easy when we're along an axis, but what if we have something a little more general like this, where start point may be the origin and the end point may be 1, 1, 1? Well, the bases are no longer on a plane that's that's along two of the axes. So we're going to have to figure out how to kind of transform these two vectors that represent the plane that the base is in to be rotated. So let's go back to the base example of going up in the y hat, or in the j hat direction. So we have our arm, and I'm just going to keep it as just a cylinder for now, because the head will the example for the head will follow. But so this is our cylinder, and we're going to call the arm vector the direction along which the arrow goes. So this is going to be, we'll call it A with the vector. So A is equal to end minus start. So this is just the direction which the arrow travels along. And then we then have a plane, which we'll call pi, and that contains the base. So pi, so we'll call the base B, and B is a subset of pi, the plane. And the way we're gonna represent this plane pi is just using two vectors, because in 3D space, to represent a plane, you essentially just need a basis of two vectors. So this is a bit more complicated stuff, but essentially if you have two vectors, so let me actually get up GeoGebra. That's might be a little more of might be a better example. 3D. So we'll create a vector going, oh no, not that. Going from 0, 0, 0 to 1, 1, 1. That's our first vector. And then we also have another vector. Nope, there we go. And this one will also start at the origin, and it will go to -1, 2, 3, like so. So we have two vectors, and you can kind of see that if I orient this in such a way, these vectors will be aligned. And then we're also going to create a plane. So we're going to have a vector n, we'll say, is equal to the cross product of vec and u. So this cross product will be perpendicular to the vectors vec and u, where those are just the two bases there. And then a little trick that you can use to define a plane here is just if you have a normal vector, and you can take the components of the normal vector and then use them in a linear combination here. So 1x minus 4y plus 3z is equal to 0. And that defines a plane. And you can see that both vectors, both of the original two vectors, are in this plane. And we have the cross product being perpendicular to the plane. And you just have to believe me here, but if we take a linear combination of the vectors, we'll call this vector v actually, just to have it, yeah. So v and u, if we take a linear combination, meaning just, so we have v and u, and I can say that pi is just defined as all the points a v plus b u, where a and b are in the set of all real numbers. So a linear combination of the vectors v and u is just adding them up, scaling them by some constant, and then adding them up. So that's the plane pi. And we essentially just need that, and this will allow us to calculate our transformation matrix, because it's obvious that we're going to need to use a transformation matrix to rotate stuff. So I guess we haven't talked about it much in the math visualizer, but the way that, so when we looked at the sphere, we were multiplying this position by a projection and a view matrix. And that's transforming the point. So all 4x4 matrices can be represented as a transformation of a 4D position into a 4D position. But once again, we just use the 1.0 for normalization. Or not for normalization, but just to keep it there. It makes certain transformations possible. So if we're able to figure out how to rotate this whole plane, we can rotate the base. And that will give us the new points that we need to represent this arrow here. So we're essentially trying to take the plane pi and rotate it so that it contains the base of the new arrow. But the thing is, how do we define that? So if our arrow is defined by a, u, and v, where u and v are the vectors in the plane of the base. Well, I mean, the way we calculated u and v was, well, I guess this isn't the way we calculated them yet, but what we knew going in is that the base is perpendicular to the arm vector. So the arm travels upwards out of the base. So we know that a is perpendicular to u, and a is also perpendicular to v. So we can call a perpendicular to any linear combination here. So a perpendicular to u gives us that a dot with u is equal to 0. So this is just the dot product. I go into a bit more, what is math visualizer like? Well, right now we just have a sphere, but we're going to create some arrows today. So it's just a bunch of simple objects, and it's a work in progress, but it's going to be some mathematical concepts. So today we're creating arrows that will allow us to represent axes, or just orient ourselves with respect to the world. But we're going to do surfaces in the next video, mathematical surfaces rather. So we know that a is perpendicular to u, meaning the dot product is 0, and the same thing goes for a and v. Now, if I take the linear combination of any vector u and v, well, so let's say a dotted with, we'll call the constants now c1u plus c2v. So the c1u plus c2v is just a linear combination. And we know that this is very similar to the definition of pi. So we're kind of testing here that a dotted with any linear combination of v and u. So i.e. A dotted with any vector in the plane pi. Well, let's just expand here, distribute, because the dot product follows the distributive property. So you have C1 times A dotted with U plus C2 times A dotted with V. What does this give us? Well, C1 times A dotted with U we know is 0, so 0 plus 0 is equal to 0. And therefore, A is perpendicular to any vector C1, to any linear combination of the two. So A is the normal vector to our plane, and now we have an equation for the plane. So if we represent A is equal to, called AX, AY, and AZ, where A is just once again end minus start, we now have an equation for the plane. It's just AX times X plus AY times Y plus AZ times Z is equal to 0. And this is just an expanded dot product. So this is just the vector A dotted with any vector we'll call P. So P is any point in the plane. And we'll just call it point, vector, the same thing, especially with the plane that goes to the origin. So A dotted with the point is equal to 0. So therefore A is perpendicular to P. So therefore A is the normal vector to the plane. So we've now figured out that with an arm vector, we can now define our translation. But the mathematics doesn't stop there. So why are we trying to calculate the two vectors in the plane? Why are we trying to calculate U and V? So we have A, but why are we trying to calculate U and V? So let's look at what a transformation matrix looks like. So we have T, which is 4 by 4, and we multiply it by some XYZ point, and we get a transformed vector. If we expand the columns of T, so if we say, not A, we'll say T1 so T1, T2, T3, and then we'll also say T4. So these are the 4 columns times X, Y, Z, and 1. Well, this is just equal to X times T1 plus Y times T2 plus Z times T3 plus T4. And given that we have a constraint where this last component in the position always has to be 1, we can also further assume that the row has to be zeros except for 1. So T4 is just some values. So these are all become 3D vectors now. And no matter how we do this, we see that this will always give us an X prime, a Y prime, a Z prime, and a 1. So this 1 has to be there. And if we further look at this and dissect this, if we let's do a thought experiment here. What if X, Y, Z? What if the vector X here is the I hat vector? So X is equal to I hat. So this is equal to 1, 0, 0. So therefore, X is equal to 1, and Y is equal to Z is equal to 0. So therefore, X prime, the transformed vector, will just be T1. So, and if you do this for each of the other unit vectors, you'll see that each column essentially represents the transformed unit vector in that axis. So T1 is equal to the transformation matrix times I hat. T2 is equal to the transformation matrix times j hat. And T3 is equal to the transformation matrix times k hat. And again, sorry, give me 2 seconds. Okay, we are good. So again, how does this help us? Well, we know now how to specify a transformation for each column or for each unit vector and how to construct a transformation matrix based on that. T4 we'll get to in a second, but let's just assume that T4 is just all zeros for now. So we now know how to build a matrix that will transform each of our unit vectors into their respective places that are into their target places. Now, okay, wonderful. What does that do for us? Let's go back to our basic arrow, where the arm vector was in the j hat direction, so A is equal to J, and I and K were the two vectors U and V in the plane. So we'll say U is equal to I hat and V is equal to K hat. All right, well, how do we do this? How do we make a transformation matrix out of this? Well, let's think about this. So this is the base case, the identity transformation, meaning we don't do anything. So if we multiply the identity matrix, which just has ones in the diagonals, by I, J, and K, we will get A, U, and V. But if we apply the transformation, or if we have a different arrow where the arm vector is not the j hat vector, well, then we want to transform. It's easy to define the points in this area just because we have a bunch of cosines and we can specify, for example, all the points on the bottom in the base of the sphere will have a y coordinate of 0, and then it just becomes a circle. So when we look at the geometry shader or when we procedurally generate vertices, all the points in this base will have a y coordinate of 0. And they can be represented, so base is just equal to all points cosine theta, 0, and sine theta. And we looked at polar coordinates last time where theta is in the range of 0 to 2 pi. So that's the base. At least the border of the base. So we're now able to give a definition of our the most basic base for our arrow, and likewise at the top, these all have a constant y coordinate. Now, knowing that we can construct a transformation matrix, by knowing where each of these vectors go, let's just replace these. Let's just apply this let's look at this definition here. So in our basic case, we have this. But in our more complex case, we have the arm vector is going to be some transformation of the j hat vector, because once again we want to start with the basic arrow and define the coordinates there and then transform it using a matrix. So we have the arm vector is just a transformation of the j hat vector, and then U is a transformation of the I hat vector, and V is a transformation of the j hat vector. And now these are simply the columns. So this becomes T2. Arm becomes T2, U becomes T1, and V becomes T3. So we now figured out if we can define A, U, and V, we have our transformation matrix. So we're essentially going to have our transformation matrix is equal to A, which is a 3D vector, U, or sorry, swapped them around. U is the left hand, A is in the middle, and V is over there. Now what do we do with this last column? Well, it has to have a last value of 1. We know that. The last column serves as a translation, so it moves it. It's the last thing that gets added. So if we know that if this last coordinate is 1, then everything will just be added. We will just add T4 to everything, and that's just a translation. Notice how this doesn't depend on X, Y, or Z, this factor right here. That doesn't depend on X, Y, or Z. So we're just going to define this as our start point, S. So the basic vector starts at the origin, but when we want to make a new arrow that starts elsewhere, we can translate it so that it actually does end up starting just using this last column here. So now so how are we going to be able to calculate U and V given only A? Well, again, we did this a little bit of math here, and we found that we have a plane, the equation for the plane. And from this equation for the plane, we essentially need to get to two basis vectors. So we have the equation for the plane, and we want this to give us a U and a V. So once again, A is equal to AX, AY, and AZ. And we need this equation to give us U and V. Well, let's look at this one way. Let's for our case, let's assume that AY is not 0. So if we hold AY constant, so I'll just say that's just a constant not equal to 0. Let's try and get the other two. Let's just try and get Y in terms, or actually, sorry, not AY. Let's just try and get one variable in terms of the other two. Let's just do an experiment here. So for example, if we do some rearrangement, Y is equal to minus AX times X plus AY times Y over, times plus AZ times Z all over AY. Just a little bit of rearrangement. We now have that Y is equal to minus AX over AY times X minus AZ over AY times Z. And this once again assumes that AY is non-zero. So if we now plug this back into our representation of all points in the plane, so pi is equal to all points let me see, what do we have here? We have X and Z, those are coordinates, just held as they are. And then Y depends on the two. So AX over AY, X minus AZ over AY times Z. And this then assumes that X and Z are in the set of all real numbers. But what is this? This is a linear combination of two vectors. So all the points in the plane have this form. I'm just going to rewrite it down here. And if we separate based on the constants, we have that this is equal to X times, because X and Z are constants, we're assuming that they're arbitrary constants. So this is X times 1 minus AX over AY, 0. Plus Z times 0 minus AZ over AY, 1. And that's a linear combination, and that's just the set of all linear combinations, and hence a plane, because it's an infinite set of vectors, because X and Z can be any number. So we have our basis vectors now. Oh, not that. We have our basis vectors as this and this, and we can then just define that as u and v. So, yeah. So, quick wrap up, and I will just go through this all again. Our goal is to create a transformation matrix like this. And we need to figure out how to build the columns. So with only given an arm vector, only given the vector A, which is the direction of the arm. So we start by defining our vertices in the basic arrow along the y-axis with the base in the xz plane. And we want to figure out how to rotate it and how to translate it so that it can represent any arrow. So we start with this basic definition here, where the arm vector is j hat, u is I hat, and v is k hat. So u and v are the basis of the plane. And then we went to look at, well, if we are just given A and we know that the base is perpendicular to A, how can we find u and v? And we figured out a mathematical definition that's down here. And we found that u and v can be represented as a linear combination. Or sorry, any vector in the plane can be represented as a linear combination of two vectors, which we then denoted u and v, which are in fact perpendicular to A. And I'll just a sanity check here. Let's do A dotted with u, so this is equal to ax times 1 plus ay times minus ax over ay plus az times 0. So this is equal to ax, and then this is minus ay, so ax times ay over ay plus 0. The two ay's cancel, and we have ax minus ax, which is equal to 0, and the calculation will be the same for v. So we know that a and u are perpendicular, and then a and v are also perpendicular. So this is just a quick sanity check. So we now have a definition for u and v. But what does that give us? Well, once again, if we just consider our basic, the most basic arrow that we're going to create, and that's how we're going to calculate our vertices, just because it's easy to calculate it when we have a constant y coordinate, well, then we just make a, u, and v the columns of our transformation matrix, and that will define how where we send the so the y-axis gets sent to the arm vector, and then the x and z axes get sent to u and v wherever they may be, and then we also translate in the fourth column using the start point. So that was a lot of talking, and I'm sorry if that was incoherent, but I can post, if people would like, I can post these notes on the GitHub. But in essence, you just need to remember transformation matrix, each column just represents where one of the coordinates is going. So the first column represents where the I hat vector goes, so on and so forth. So we have a model matrix, and we're essentially going to just pass this into the vertex shader, because if this stays constant for our arrow, then this is going to be a static instance of an arrow, so it's not going to move anywhere. So this matrix is going to stay constant. So if we had to do this calculation every time for every vertex in the vertex shader, that'd be a waste of computational power. So what we're going to do is we're going to just pass this in through the VBO, just like any other object, and we'll see how we do that. But we're going to pass it in with the VBO as the model matrix, or the transformation matrix. So let's get started. So we're going to go into programs in that folder, and we're going to create a new item called arrow.hpp. finally typing. All right. Good. Sorry. I'm just getting paranoid. My microphone wasn't working earlier this week when I was trying to record a video, but it's working now, so we are all set to go. All right, so we'll start with some includes. So we want to include glad/glad.h, include glfw/glfw3.h, and then we're going to include glm because we'll need some vectors. We're also going to need lists because we're going to render the arrow just like we did with the sphere. So where we're going to have different instances. So we're going to need to store a list of each position, offset, size, and so on. All right, then we're going to include program because we're going to inherit that. Include /rendering/shader.h. Include /rendering/material. So we're actually going to do the material this time. Include rendering/vertex memory. And I believe that's it. Yes, that's all. All right, then we'll do our macro. So if not defined, arrow HPP, define arrow HPP, and if. All right, so that's our macro. And then we're going to define our class now. So class arrow, and it inherits public program. So as with the sphere, we're going to have a bunch of lists. So there we're going to have to bound those lists just so we don't have a million instances. I mean, I suppose we could, but why? Well, we're just going to bound it just to make sure that we don't. So we'll have a standard vector. So to keep things compact, we're going to compose our dimensions into just one vector. So a list of floats, essentially. We're not going to use it as a vector for calculation. We're going to decompose it into its individual floats, but still. So it's going to be a list of 4D vectors, dimensions. And this is going to have the magnitude, the arm radius, the head radius, and the head height. And then we're going to have a standard list of glm vec4 never mind, actually, not vec4 just yet. We're going to have a 4D matrix, which are going to be the model matrices. So these are going to be the list of model matrices, and we're going to see how we pass these in through the VBO. And then we're also going to want something called a normal matrix. So this is going to be a standard vector of a 3D matrix, so map3. And these are going to be the normal model matrices. And what these will do is these will allow us to calculate a transformed direction. So specifically a transformed model matrix, or sorry, a transformed normal vector. And we will see what the normal vector will be, and it will become apparent what it is. But that was my back, if anyone heard that. Just cracking in a million spots. But yeah, so this normal model matrix will be a 3D matrix, and it will transform a normal vector into a new space. And then we will also pass in a standard list of diffuse colors and a list of 4D vectors for specular colors. So this will be the specular and the shininess constant. And this is also done in the sphere class. Now notice how with the sphere we needed to pass in offsets and sizes. Well, here the offset is packaged into the model matrix. So that offset is just that last column, and once we multiply it by the point, we won't even need to do the plus offset. It will just be packaged in there. So this makes it much easier. And then we also have our array object VAO. All right, so we're going to have public here, and it's going to constructor arrow unsigned int max number of instances as the only parameter. And then we just initialize our two variables. Max number of instances is max, just the value. And then number of instances gets initialized to 0. And then we're going to do void load. Let me actually just zoom in for you guys here. So load is not going to be where we calculate. Actually, I suppose we have to do something first. Yeah, add instance is first. So we're going to have return type boolean, and it's going to be called add instance. We pass in a glm vec3 start, a glm vec3 end, float arm radius, float head radius, float head height, and then we will also have a material for the color. Bunch of parameters. So start point, end point, arm radius, head height, and then material for the colors. We're first going to do a bounds check. So if number of instances is greater than or equal to max number of instances, then we just return false. And otherwise, we're going to start with our matrix calculation. So calculate model matrix. So this is going to be where we employ the mathematics that we just went over. So we're going to have a glm mat for mat, and it's going to just be an identity matrix. So we started with ones in the diagonals. And then we want to calculate our arm vector. So glm vec3 arm vector, and we're just going to do everything in normalized coordinates. So glm normalize end minus start. So that's just the arm vector that we have up here. Except this time it's going to be in normalized coordinates. And that's why we're going to be passing in the magnitude as a dimension. All right, and now we need to get our two vectors, b1 and b2. That's what we call u and v here. So glm vec3. We'll just say u and v. So these are going to be the basis vectors of the plane that contains the base. So the calculation that we did over here assumed that AY was non-zero. So the arm vector did not change in the y direction. The IE is in the XZ plane. Now this becomes a problem when we have axes like the x-axis and the z-axis that explicitly define the XZ plane. So AY would be 0 for those two. So therefore we need to have a few cases. And it turns out that no matter which way you define these or no matter which variable you isolate, it becomes the same. Because this will still just be a linear combination of two vectors. It's just going to change which coordinates are where. I'll just run through it. The second example with where we isolate x. So let's say x is equal to minus ay over axy minus AZ over AXZ. So this gives our points. So we have minus AX over AYY. And then for Z, oops, sorry, I miswrote those. And then Y and Z. And then once again, this just decomposes into a linear combination where Y and Z are just held constant and can be any real number. So once again, two basis vectors. And the example is the same if we isolate Z. But no matter what we do, you can see that it doesn't matter what coordinate we use. They're going to give us the same vectors. Or at least we'll be able to find two basis vectors of the same plane. And then as long as we place them in the correct columns, that will give us our proper transformation matrix. So we have to do some cases. So if arm vector dot y is not equal 0, so therefore we can isolate y as some value, and I will add in some more comments, but point is u is going to be equal to glm vec3 1.0 minus arm vector dot x divided by arm vector dot y 0.0. V is equal to glm vec3 0 minus arm vector dot z divided by arm vector dot y 1.0. So that's the first case. And then we do else if arm vector dot z does not equal 0.0. So u is equal to glm vec3. So this time we isolate z, and this will just be 1.0, 0.0, and then minus arm vector dot x divided by arm vector dot z, and then v is equal to glm vec3 0, 1 minus arm vector dot y divided by arm vector dot z. So once again, this is just following the same format where we just have two basis vectors. And then else if arm vector dot x does not equal 0, then u is equal to glm vec3. It's going to be minus a dot y divided by a dot x 1.0, 0.0, and then v is equal to the other one. So minus a dot z divided by a dot x 0.0 and 1.0. And you might just be wondering, well, Michael, how do we know that these two vectors are independent? If we need a basis, if you're curious and if you like questioning me, which you should, how do we know that that vectors u and v are independent? Well, let's look at them. Is there any constant that we can multiply this vector by to get to the other one? Because that's the definition of linear independence. If there isn't a constant, so just as a general definition, u and v are linearly independent if and only if the only constant for which u, so k times u is equal to v, if and only if k is equal to 0. So this constant essentially doesn't exist. So this is the trivial example. Wait. No, sorry. Wrong definition. A times u plus b times v is equal to 0 if and only if a is equal to b is equal to 0. So the only linear combination of u and v that gets us to the 0 vector is the trivial one with 0 constants. And this does work, because if you just look at the columns, there's no way, well, this essentially just equates to u is equal to minus b over a v. And if this constant doesn't exist, so u is equal to kv, and if this constant doesn't exist, then they're linearly independent. I.e. a is equal to b is equal to 0, so the constant is just 0 over 0, which does not exist. And you can just look at this. Well, if we multiply this by the first vector by k, so k times minus ay over ax 1, 0 is equal to minus kay over ax k and 0. And there's no value of k for which this can equal the other one, minus az over ax 0, 1. Maybe we can get the top coordinates to match, but k cannot be 0, because that doesn't exist. And 0 never equals 1. K equals 0 is trivial, and 0 cannot equal 1. So these are linearly independent, and you can just do that by matching up the components of the other vectors for the other cases as well. All right, so we now have our 3 vectors, and then we also just want to have the last case, so else. So if all vectors are 0, or if all components are 0 of the arm vector, then the 2 points are the same. So like the start and the end points are the same. So we return false. So once again, I will add more comments to the code before I commit, but this is how we're going to do it. So we're going to set each column of the matrix. So in GLM, you can just do the square brackets represent an indexing into the columns. So we're going to set the 0th column to GLM vec4, and we're going to normalize B1. So GLM normalize B1 and 0.0. And then mat at 1 is equal to GLM vec4 arm vector and 0.0. What am I getting here? Oh, not B1, is U, sorry. And then mat at 2 is equal to GLM vec4. This is going to be V, so we normalize V, and the last component is 0. And then the third column, mat at 3, is equal to GLM vec4, and once again, this is going to be the translation component, so it's just the start and 1.0. That last component has to be 1.0. And then we add our values. So mats.pushback, or sorry, model mats dot pushback the matrix. And then for the normal matrix, I'm not going to go into depth on the calculation here, but it's essentially the transpose of the inverse of the matrix. So normal mats.pushback, wait, is that a thing? Normal model mats. So dot pushback. So we take the GLM transpose of the GLM inverse of the 3D matrix of the conversion of mat. So let's look at this calculation. So we first convert the 4D matrix into a 3x3 matrix. So we just take the upper left 9 entries, then we take the inverse, and then we take the transpose. It turns out that this operation, if mat is orthogonal, then this will just be the original matrix. So that means if the columns of the 3x3 matrix are all perpendicular to each other, then this will just be the original. But I don't think that's true for us. If we take the dot product of u and v here, we get minus ay, or we get ay times az over ax squared. That's the dot product, and that's not 0, unless it's along one of the axes. But even then, we can't guarantee that. So we're just going to take this, but this is a one-time calculation, so it's okay. I will post a link down below for how normal matrices work, normal model matrices work. All right, and then we have our dimensions. So dimensions.pushback. So the 4 components are going to be the magnitude, so GLM length of end minus start, the arm radius, the head radius, and then the head height. Oops. Uh-oh. No, what are we doing? What are we doing? That's not what I wanted to do. So let me just make sure that that's consistent. Arm, head, head. Perfect. So those are the 4 dimensions. And then we're going to do colors dot, oops, not colors, sorry. Diffuse dot pushback. Mat dot diffuse, right? Or is material not a, it's just called material, sorry. Material dot diffuse. And then we say diffuse, or sorry, specular dot pushback. GLM vec4, so we need to convert material dot specular to a vec4 with shininess. Sorry, material dot shininess as its final component. So that's all the data that we need for each instance. And then we increment number of instances and then return true. So once again, comments will be added if you're lost in the code, but let's look over this. Arm vector perpendicular to the plane containing the base, and then we just calculate 2 vectors that are the span for the plane containing the base, and that's our rotation matrix. And then we designate where each of the unit vectors will go, so I hat, j hat, and k hat, and I hat and k hat are in the base, and we rotate them and do whatever, and then the arm vector just, and then the j hat vector gets just rotated with the arm. And then we pass in dimensions and colors. All right. Now for load, this is going to be fun. So for load, we're going to start like we did with the sphere. So we say the shader is equal to a shader, no default header, and we're going to pass in shader paths here. So for the vertex shader, we're going to create a new one, so arrow.vs. Fragment shader, we're going to call as sphere.fs. Actually, we're going to rename that later. And then the geometry shader will be arrow.gs, and we are going to be using a geometry shader. So the fragment shader for the sphere can be used for any directional light or any object with a directional light. We just need to pass in these values here. And the texture coordinate isn't really going to matter at all. Not sphere, arrow. There we are. So we create our shader. Then we need to generate and bind VAO. Then we need to set up our VBOs. So VAO at, so once again, all the, we're not actually storing any vertex data. So we're not storing the points on in a list here. So what we are going to do is we're going to calculate them using the geometry shader. And therefore, we can just bypass instancing and render one quote-unquote vertex for every instance. So it's not going to be an actual vertex. it's just going to be, we're going to render one unit with the GPU, and that unit is going to be an instance. So we're going to be bypassing instancing. We don't need to refresh or reset any counter. We're just going to pass in all the values without instancing. So VAO at dim VBO is equal to a buffer object, GL array buffer, and then we're going to say VAO at dim VBO dot generate dot bind, and then we're going to do dot set data. So we're going to pass in the data, and that's a bunch of GLM vec4s, and its number is going to be number of instances. The data is going to be a reference to dimensions at 0, and it's going to be GL static draw. And then just set an attribute pointer. The template is going to be GL float. And we're going to say index 0, size 4 of GL float, and we have to stride 4 floats to get to the next element, and then the offset is 0, and we don't specify a divisor because once again we're not instancing, even though we are using instances. All right, next we're going to do the matrices. So this is going to be where things get a little more complicated. So the VBO we're going to call is just mat VBO, and I'm going to replace that there. And it's still going to be a GL array buffer, still going to generate, still going to bind. The data is now going to be GLM mat4, and we need it to point to model mats at 0, so a reference there. And then the attribute pointer is going to be a little different. So in our vertex shaders, each of these layouts can store a maximum of a 4D vector. So a vector with 4 elements. It can't store a matrix. So the way you get around this is just by specifying multiple attribute pointers for the matrix. So essentially the matrix is going to take out location 2, 3, 4, and 5. So we need to set the corresponding attributes. So at pointer at 1, and it's still going to be a 4D vector, so the rest of the parameters can stay the same. So it's going to be index 1, 2, 3, and 4. So we have 4 rows, or 4 columns rather. And then something similar for the normal model matrix. So we'll just do this from scratch. So VAO at norm VBO is equal to buffer object, GL array buffer, VAO at norm VBO dot generate, VAO at norm VBO dot bind, dot set data. This time it's going to be a GLM mat3 3x3 matrix. Yeah, so the data is going to be number of instances again, and then the pointer to the data is going to be normal model matrices at 0, and then GL static draw. And then now for the attribute pointers, there are 3 columns, so we're going to do 3 attributes. So VAO at norm VBO dot set at pointer, it's going to be the same type argument, so GL float. This is going to be index we just pick up after the model matrices, so index 5. It's going to be 3 GL floats. And to get to the next one, I actually made a mistake here. These attribute pointers should be not GL floats, but for the model matrix, they should be GLM vec4s, because that's what each element is. And to get to the next 4D vector to pass in, we need to increment by 4 4D vectors, not 4 floats. This 4, the first 4, corresponds to this type. So 4 GL floats, and then 4 4D vectors. And then for the attribute pointers for the normal model matrix, it's going to be GLM vec3. So index 5, 3 GL floats, and we need to jump 3 GLM vec3s to get to the next one. Essentially skip over the rest of the matrix. And then we do 5, 6, and 7 for the indices. And then now we have colors. So I'm actually just going to take the dim VBO and copy and paste it. And I'm going to rename it diffuse VBO. And it's going to be, data is going to be 3. So a 3D vector. So we need to 3 GL floats, and we jump 3 to get to the next one. Oh, sorry, this should be a reference to diffuse at 0, and then the same thing for specular. And this, we need the index of the diffuse to continue after, so index 8 and then index 9 for the specular. One thing to note actually is that we can only do this if we have instances. So these pointers will only be valid if we have instances. So we essentially need to say in load, if not number of instances, just return, because we cannot generate and bind a VAO and set up data because these pointers are invalid. All right. So we have the load, we have add instance, and now we need to write the render function. So void render, we're going to say shader.activate, shader.bind, and then we're going to do VAO.draw. So once again, we're going to be drawing one quote unquote vertex or one just unit with the VAO for every instance. So the mode is going to be GL points. We just want to draw one at a time. And then the first value will be 0, and then the count will be number of instances. Simple as that. Sorry, this should be VAO.bind. And then for cleanup, it's simply setting number of instances is equal to 0, clearing our lists, and then cleaning up the shader and VAO. All right. So that's the arrow class. Let's just go ahead and or you know, we'll do main.cpp later. Let me go refill my water before we start with the shaders. And this will be kind of another topic. I suppose I could have divided this into 2 videos, but we'll just keep going. And I'm back. Got a piece of candy. We're good to go. Okay. All right. So we just finished writing the arrow class. We have our vertex buffer objects set up, and we are now good to start writing the shaders where we are actually going to, thank you, Harvey. We're going to write the shaders where we're going to calculate the vertices. So the calculations that we did up here with the basis vectors, this is only one part of the calculation. So this is the transformation part. We next need to generate the vertices, and it's going to involve trig, like as with the sphere. All right. So we're going to, in our shaders folder, we're going to create a new file called arrow.vs and arrow.gs for geometry shader. All right. So we'll start with the vertex shader. So version 330 core, as with before. And I still haven't installed the extensions as someone told me to do last time. I need to do that. All right. So we have our layout variables as specified by the VBO. So the first one is layout location is equal to 0, and it's in vec4 dimensions. Remember this. This sets up these have the 4 dimension parameters. And then we have layout location is equal to 1, and this is going to be our model matrix. So in mat4 model matrix. And remember, this takes up 4 slots. So we next need to jump to layout location is equal to 5. And we calculated that up here. So 1, 2, 3, 4, and then 5, 6, 7 for the next matrix. So this is in mat3 normal model mat, and then layout location is equal to, that's 5, 6, 7, so 8 in vec3 diffuse, and layout location is equal to 9 in vec4 specular. And then we're going to output to the geometry shader, so out vs out. So we want to send enough information to the geometry shader so that it can effectively, why didn't I use my math library? I definitely could have. GLM just makes things so much easier. Math library is in C, so I could have, but GLM just is much cleaner than mine. And it just, the math library is built in C, so there's no constructors and there's none of that. But with GLM, it just makes it so simple and so easy to do it. But yeah. So we have VS out, and so we want to pass enough information into the geometry shader so that it can generate all the vertices and transform them properly. And that turns out that we just want to pass in all the data. So each one of these vertices is an instance. Every time the vertex shader gets invoked, we get a dimension vector, a model matrix, a normal model matrix, a diffuse color, and a specular color with shininess constant, and that represents a singular instance. So we just want to funnel all this data into the geometry shader. So we can communicate with the geometry shader, not using in and out variables, but by using this structure here, vs out. in the keywords in and out send stuff to the fragment shader. So we're going to have a float magnitude, and this will be the length of the arrow. Float radius, or arm radius. Then we have the float head radius, and then float head height. And then we do a mat4 model and a mat3 normal model. And then we need to pass in colors. So vec3 diffuse and vec3 specular, and then float shininess. So we just need to populate these values in the main function. So void main, we're first going to start with the first four, which we just essentially send in values from the dimensions vector. So vs out.magnitude is equal to dimensions.x, vs out.radius, arm radius is equal to dimensions.y, vs out.head radius is equal to dimensions.z, and then head height is equal to dimensions.w, or the fourth component. And then vs out.model is equal to the model matrix, and the normal model is equal to the normal model matrix. I forget how I named it. And then for the colors, we have diffuse is equal to diffuse, and then specular is equal to specular.xyz. So the output is a 3D vector. We pass in a 4D vector, which contains the specular color along with the shininess. And then we say vs out.shininess is equal to specular.w. And I suppose we can just call this RGB. I think that works with, we'll test that afterwards. But the first three components go to the specular color, and then the last one goes to the shininess. And I guess I will also try afterwards just using the output keyword from the vertex shader to send it to the fragment shader. Let's see if that works. Okay, so fragment shader is all taken care of, and then the geometry shader. This is the fun part. So this is something that we haven't seen yet at all. So we're going to have a version 330 core. And then we're going to need the variable or the value pi. So we're going to define mpi. We're going to say, so let me do this from memory. It's 1415926535. And that's all I can remember. But I have, I swear I wasn't looking. There's 8979323846, and you know, who cares about the rest? Alright, so then we're going to take in some points. So the way the geometry shader works is it takes in some values. You can specify how it does, and that's done through the layout variable. So layouts, and you can specify points, triangles, and I think lines. Points is just you take in every point from the vertex shader. Triangles is you take in a group of 3, and then lines is you would take in a group of 2. So we're going to output triangles, and we need to specify that. So layout, and we're going to say triangle strip, just because this allows us to not have to duplicate vertices, and we can just when we don't duplicate the vertices, then it'll just fill in triangles with vertices that we give it. So for example, if we were to give it so triangle strip essentially if we pass in these 5 dots, it'll just build triangles that will fill in the space like that. So that's triangle strip. And then the max vertices, well, we have to be a little careful here. I'm going to say a number 56. And you'll see why. This, I didn't know this coming in. I had to test it and calculate it given the numbers that we were looking at, but I'll show you why it's 56 vertices. And then we're going to take in all the values from the vertex shader. So I'm just going to copy the structure here and just rename it to in, and I'm going to call it, it's still VS out as the structure name, and then we're going to call it GS in, except now we have to take it in as an array, because once again it may be layout triangles, and in which case this array would be a length 3, but since we're doing just points, it's going to be an array of length 1. Sucks, but it's still an array. And then we need to output stuff to the fragment shader, so I'm going to take that in here. So I'm just going to copy all those values, and I'm just going to make the in keyword out. And then we also take in a uniform value. Oops. Oh, I changed my keyboard. Uniform map for projection view. So we can write to uniform variables in the geometry shader just like we can with the other ones. All right. So how are we going to draw this arrow? So we kind of saw with the sphere that we have no choice but to approximate it using triangles, and we can only have a certain resolution. With the arrow, it's going to be so small that we can get away with having less vertices. So we're going to define our resolution as the number of edges, and this will be some value, and that will essentially define the fineness here. So this is essentially our angle step, and we will calculate, that's the worst circle, oh my lord. All right, circle, no, circle, big. We're essentially going to approximate this using a certain number of edges. So something like that, that. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So 13 edges. And you see that looks pretty good. So that's going to be the base. We're going to approximate each circle with 15 edges, and that goes for the base of this cylinder and also the base of the cone for the head. So the cylinder has a circle, and then also the head has another circle as the base. Like so. And we're just going to use the same number of edges on the two. So essentially, for the cylinder, it's going to be relatively simple. We just need to pass in. So this point will start here, this point, and we need to pass them in for y is equal to 0, and also y is equal to some height. I'll call h, and we'll define what that height is. Yeah, so so yeah, 0. So that essentially the way we calculate these vertices is going to be in the XZ plane, so they have constant Y values. And then, so that'll be the base of the circle for the base of the cylinder, the top of the cylinder, and also the base of the cone, because same Y coordinate. And then for the top of the cone, it's just going to be 1 point. So we will specify this point, and then the center at the top at some other height that's different. And then it'll essentially do something like this. So this is what the circle is going to look like. But you can imagine that for our cone, this center will be raised. It'll be elevated. So I'm not going to try and draw it. I can't draw 3D. And then these points are going to be calculated using cosine and sine, as we did with the sphere. Okay. So I'm going to have so we're going to have a constant here. Integer number of edges is equal to 15, so we can customize that. And then we're going to have a function send vertex, which is going to take in a vec3 position and a vec3 normal. And we're going to look how to calculate the normal in a second. But we're first going to calculate the transformed position is equal to model times vec4 position in 1.0. And this is set to the fragment position, or actually we can just say, we can set fragment position is equal to model times the position. Wait, no. Hold on. Nope, that doesn't work. The transformed position is equal to the 4x4 matrix model times the vec4 conversion of the position. And then we set the fragment position is equal to the transformed position dot xyz, because the fragment position going to the fragment shader is just a 3D vector. It's the position in the world. We don't care about that last point. And the normal is equal to the normal model times norm. This gets sent to the fragment shader here. So we have fragment position, normal, and then we'll set text later, but then GL position, so this is just the output to the GPU saying, hey, this is where we want you to draw the thing. So GL position is equal to projection view times the transformed position. And then we will emit a vertex. So emit vertex essentially just sends a vertex to the GPU to be processed by the fragment shader. All right, so we're going to split this up into two. Sorry, this should not be model and normal model. This should be GS in at 0 dot model, and then GS in at 0 dot normal model. Once again, at 0 because it's an array and we only have 1 point. All right, so then we're going to have our two functions. So this will be void build arm, or we'll say cylinder, and it's going to have a float height and a float radius. So this is essentially building a cylinder up the y-axis, and then we also want to build a cone. So void build cone, float head radius, magnitude, and head height. So the magnitude is essentially the top of the cone. So the magnitude is the point, and head height will be how far below it extends. And then for main, we're going to send some data to the fragment shader. So diffuse is equal to, I think The sphere's fragment shader wants everything in a vec3, so diffuse is equal to gs in at 0 dot diffuse. Specular is equal to gs in at 0 dot specular. And then shininess is equal to gs in at 0 dot shininess. And then we just want to call the build functions. So build cylinder. The height is going to be gs in at 0 dot magnitude minus gs in at 0 dot head height. And the radius is just the radius passed in from the arm radius from the vertex shader. So gs in at 0 dot arm radius. So the height of the cylinder, we don't want it to go all the way to the tip because once again we have the head of the arrow. So we want it to go up until, so however far below the point that we want the head to start. And we'll see how we can play around with this and make it pretty fun. And then build the cone, which is, for the head radius, it's just from the vertex shader, so head radius. And then the magnitude is the magnitude. And then head height. All right, so this is all we need to do in the main function. Pass in values to the, actually we need to set text core to 0. Just because we don't really care, but we need to output something. So text is, it's actually just called text. Okay. We could look at textures, but I'm not going to do it right now. All right, so we'll start with building the cylinder. That's the easiest one. So we start with our increment, or the angle step, as we looked at in the sphere's vertex shader, or the sphere's vertices. So float increment is equal to 2 times m pi divided by the float value of the number of edges. So we essentially just take the whole circle, which has 2 pi as its the angle to get from around the circle in radians, and then we divide that by the number of edges to get the angle step. Then we're just going to iterate. So float I is equal to 0.0. I is less than the float of the number of edges plus 1.0, and then I plus equals 1.0. So we essentially wanted to write every vertex and then also wrap around, just so we have a complete arrow, a complete cylinder. So that's why we do the less than the float here plus 1. All right, and then we're going to get a current value, and so we're going to get the coordinate in the y equals 0 and then the y equals height points. So vec3 current xz is equal to, so the vec3 is going to be, we're going to do radius times the cosine of I times increment. So this was from polar coordinates. Where are we? So we can essentially parameterize a circle by x is equal to cosine t and y and z is equal to sine t, as we saw last time with the sphere. And then we just need a step for t, which is why we're doing I times the increment, which is the value of t. And then the radius just scales it so that it actually gets to the radius. And then the y coordinate will be 0, and radius times sine of I times increment is the z coordinate. And then the normal vector, well, if we have a circle, where's the circle? Did I draw a circle? I drew a circle. No, I didn't. To calculate the normal vector, like the sphere, it's just going to be the position. So we're just going to pass in vec3 norm is equal to current xz. And that's going to be regardless of the height, because it's still just going to be pointing outwards from the cylinder. So if you can kind of think about it, we have our cylinder with the top and the bottom. Oops, that's a bad. So the normal vector here is going to be pointing out, and that's also going to be the normal vector here. So it's not going to matter on the height, and it's just going to be based on the coordinate. So normal is equal to the current xz value. So then we're going to send the vertex, current xz, and norm. And then we also want to send the value at the top, so send vertex. It's going to be a new vec3 of current xz.x, the height this time for the y value, and then current xz.z, and then the normal. Same normal again. And then these values will get transformed and translated appropriately so that it represents our arrow. All right, and then afterwards we just want to say end primitive. So using triangle strip, we technically never have to call end primitive. However, since we don't want the cylinder and cone to connect, so essentially OpenGL will continue to connect. Where was it? I don't know. I think I deleted it or erased it. But as many times as we call emit vertex, OpenGL will connect them if we use triangle strip with new triangles and fill all these triangles in until we call end primitive. So we have to make sure to call that so they don't connect the head and the cylinder, because it would only be in one spot. All right, so now we're going to build our cone. So the increment is going to be the same calculation. And we're going to do the same for loop. And then we're going to calculate an xz coordinate as with before. And it's going to be the same calculation using cosine and sine, except the radius will be head radius. And the y coordinate will now be the bottom of the cone. So it's going to be the magnitude minus head height. And we saw that up here. So the length here is the magnitude, which is the magnitude of n minus start, minus head height. So we're going to say mag minus head height, like so. And then the normal, well, it's going to be a little different this time because we have a slope involved. So we have our cone and it looks like that. Can I zoom in? I can't zoom in. Actually, I can make this bigger, which might be helpful. So that's our cone, right? And we have a bunch of points and they have some angle step, like so. And the normal vector in the xz plane, so it's going to be pointing out like that, except it has to point up a little bit. So it has to point something like that. So believe me when I say this, but the xz values will be the same as with as if it was just a circle. So it's still going to point outwards. So the position is like this, and then the normal to the surface, to this little, to that surface there is still going to be, the xz values will still be the same as if it was just a cylinder. It's the y coordinate that changes because we have a sloped surface. So let's just look at this real quick. If we want to find the value the vector perpendicular to this line, and we know this, and we know this, and we know that this is, it drops by head height and moves to the right by head radius. This is just a line with a slope, and we can just easily find the perpendicular value by taking the reciprocal, or the negative reciprocal. So this value, it points upwards. So we can essentially have it go like 1, and then it'll move up by some value n, which will be the y value. So essentially the radius, or it has to have an xz distance, or an xz magnitude of 1. So we just need to use cosine and sine there. So this is equal to cosine of t plus sine squared t. But this n value is going to depend on the slope. So the slope of this line is equal to minus head height. So I'll do h over r. We'll just say h and r. So that's the slope. The slope here, m prime, is equal to the the negative reciprocal. So minus 1 over minus h over r, which just simplifies to 1 over h over r, or r over h. And we can find the y value using, I forget what it is. But we can find this value n, because m prime is equal to n over 1, so m prime is just n. So n is equal to r over h. And that's the y coordinate. How do I design the architecture of my game engine? That's a wonderful question. I kind of just started small with making sure I knew how to render stuff, and then I kind of just added classes and added abstractions where it became convenient. So for example, the first iteration was kind of like this, where we created model classes that stored a collection of vertices that we would use, and then we had a shader class, and we had a camera class, and just all these things that would be reused / we wanted to use as objects. And then the scene became a class, and the octree was a class, and it just made things a lot easier and a lot more compartmentalized and more convenient to use as a class. So that's kind of how I designed it. But for the organization, it's all over the place. I need to organize the files in like their respective directories a little more. But yeah, so we have our xz coordinate, and now we have the normal, which is equal to cosine of I times increment, and we're going to say minus 1.0 divided by minus head height divided by head radius, just to emphasize that it's the negative reciprocal, and sine of I times the increment. And I will also add a comment there. So we're going to send this vertex, current xz, and the normal, and then we will also send the head. So send vertex vec3 0.0 magnitude and 0.0, and the normal as well. We're just going to assume that they have the same normal vector. This thing here, we're assuming the tip of the arrow in its untransformed form is just on the y-axis at the magnitude. That's why we say 0 magnitude 0. All right. And a quick optimization here is that we don't want to send the head every time, just because it's not efficient. The geometry shader will interpolate, or triangle strip will interpolate, so we can just have a boolean to have it send every other time. So essentially, we can send the first vertex and then send the head and then send the next vertex, and it'll draw this triangle. And then we calculate the next vertex, but it'll still fill this in without us having to send the head. But if we draw the next one, we're going to have to send the head over. So we're going to have a boolean, bool send head is equal to true, and we'll just say if send head, I can make a sex joke here, but that would not be very family friendly, now would it? So we send the current XZ coordinate and the normal. Send the head, and then we just invert that boolean. So send head is equal to negative, not send head. And then afterwards we end the primitive. And that is that. That is the geometry shader. So geometry shader is super fucking cool. You give it how many of the vertices you want. We're giving it a point, meaning it just takes in one vertex. So we have a GS in here of an array, but it's just length 1. And we're just using all these values to calculate our coordinates. So we build the cylinder in its basic form. So the first thing we did today was we looked at how to construct our arrow, and it's with a cylinder and a cone. So we build that in along the y-axis, and then we transform it using the stuff that we calculated and passed in through the VBOs. So let's try this out. Let's go into main.cpp. Let's include the arrow program/arrow.hpp, and we're going to have arrow, and we'll have 5 arrows. So let's add a few arrows. So arrow.add instance, and we will do a glm vec3 from 0.0 to 1.0, so 0, 0, 0 to 1, 1, 1. Arm radius, this is in world value, so it's not a proportion, it's just a raw unit value. So arm radius we'll say is 0.05 f. Head radius, we'll make it a little bit bigger, 0.1. Head height, we'll make it 0.05. And the material, let's make it chrome. Why not? And then we just need to push back programs.pushback arrow, and it will do the rest if you remember. So we just push it back to the program list. It gets loaded in this for loop. We set up the directional light in this for loop. We then update it in the for loop, and we render it in the for loop, and then clean it up in the for loop. So we just need to add it to the program list, and it will get automatically rendered. I'm going to drop the rectangle for now, just because I don't want to render it. But let's look at this. Error. Wonderful. Okay. So geometry shader. We have 46. Line 46. Yes. I had a syntax error. 48 undefined variable current x z. Oh, it didn't just like it. 62. It didn't like because I messed up some colons. Oh, more. Undefined variable, diffuse and specular. Where did I? What does it want? Diff map and spec map, that's why. So the output colors from the geometry shader have to be diff map and spec map. Error again. I make sure to capitalize as you needed. And it's not rendering. Oh, wait, did I? So max vertices, I never explained this 56 number, but it's essentially just the number of vertices that we need. So 15 edges, that's GL, I know. I need to install that extension. It's really bad because I've been told like 8 times no. And I shall. But I think it'd be really funny if I didn't. 56, so we have a cylinder, so it has 15 edges, so we have 16 points in the base, 16 points in the head or the top, so that's 32, plus the head has 16 points in the base, and then 8 tips because we send it every other time, so that's 24, so 32 plus 24 is 56, so that's that number. Let me do a quick debug here. Arrow has alright, so it has an instance. What did it do? Alright, so we need to re-render arrow. I don't know if it likes our shader. This is going. This might be another shader issue. Let me just put a new line there, and a new line there. Nope. This is so embarrassing. Let me have the fragment shader just have a constant color just to see if that's the issue. Nope. So I don't know if is the geometry shader getting invoked? Let me make sure that these are getting called correctly. Okay, we push that. Number of instances plus plus. Now to load, let me make sure that this is actually getting generated properly. So we have arrow.vs, good. Ooh, sphere.fs, good. And then arrow.gs. Now let's make sure this works. So shader has a value, so that's good. Let me delete it. Okay, link program. No errors. It would have to be something here, no? Because all these lists have size 1. Does the shader take the program? Yeah, there's the shaders all. I know the shader class works. I know that for sure. No, these are 2 separate shaders. Yeah, I know for a fact that these are 2 separate shaders. But last time the problem was that this didn't have a new line, so it read this as the end of file or something like that. but it just took that, which is weird. Let me just redo my logic here. All right, so shader, generate bind, array buffer, generate bind, set data, 4D vector, dimensions at 0, set attribute pointer 0440, matrix VBO, GL array buffer, generate bind, number of instances, model matrices at 0, static, 1, 2, 3, 4. That looks all good. And it's the same for the normal matrix. Ah, yes. Aha. I have found the problem. These need to be offset by some value. Okay. So the attribute pointer for the second vector needs to be offset by 1 GLM vec4. So this is in the VBOs for the matrices. So we just need to increase the offset by 1 every time. So it offsets by 1 GLM vec4 to get to the next column. And then the same thing for the model matrix. So 0, 1, 2, 3, and then 0, 1, 2. Now, come on. Don't be shy. No, I thought that was it. I really did. Okay. So it's not the fragment shader. So 5, 6, 7. Am I reading that properly? This is 1, 2, 3, 4. This is 5, 6, 7. That's 8, and that's 9. That's good. Is this correct? Magnitude, arm radius, head radius, and head height. Okay, that's the proper order. All right, let me just go back and here and make sure this is all correct. Generate bind. Generate bind 8. No. Why did I make this dimensions? That's stupid. That should be specular. I doubt that would have any effect. If that, no, it doesn't make the difference, all right. So rendering, it's GL points, 0 number of instances. All right, I just want to make sure that the data is getting to the geometry shader. So what I am going to do is we're going to make a rectangle. So I'm going to say we're going to comment out these two, and we're going to send vertex vec3 0.0, and the normal is 1.0. So it'll be in the positive x direction, so this needs to stay there. All right, let's run this to see if it's rendering a rectangle. Okay, it's not getting to the geometry shader. Or Let me see that. I don't think it's calling anything really. So the arrow's vertex shader. It takes in 0 vec4 dimensions. Then a 1 4D matrix, which is 1, 2, 3, 4, 5, 6, 7 for a 3D matrix. 8, 9, that's all good. There's no syntax errors. We're going to output magnitude, radius, head, height, model, normal model, diffuse, specular, shininess. And we set those values accordingly. Okay. I'm not sure it's calling the shader. Let's just see if it compiles everything properly. Arrow.vs, arrow.gs, sphere.fs. Okay. Let me try something here. No, this would... Let me see if it's actually rendering in the arrow. Because that could also be a problem. No, it is rendering. Activate the shader, bind the shader, or bind the VAO, and then draw. I saw the sphere somewhere. There it is. Alright. It's weird that we're not getting a single vertex. Alright. I'm not going to keep you guys any longer. It's sad that, again, I cannot produce on the results. But I'll find the error and we'll figure it out, and I'll put a comment, or I'll update the description of the video once I got the fix. But everything else works, or the math is all correct, I know that. So yeah, I don't know what else there would be to do. I'll just walk through the code one more time, but until I see you guys again, I hope you guys enjoyed this. Hope you learned something. If you guys want the math stuff, I can post a PDF with it. But until then, enjoy yourselves. And if you find the error, tell me, please. I'd appreciate that. Or if anyone succeeds in doing it, then I would love to hear. But yeah, until I see you guys again, stay safe, and yeah, I'll see you guys next time. Have a good one.